Let's summarize Newton's laws of motion. Newton's first law gives us the idea of resistance to change in motion. The inertia is measured as mass or inertial mass. The second law gives us the idea that the change in momentum is proportional to a change in motion. And then the third law gives us the idea that momentum is conserved always. The first law, the law of inertia, giving us the idea that the resistance to change in motion is based upon mass, gives us the idea and the concept that mass is a resistance to change as opposed to mass being something that's taking up space. A change in momentum being proportional to a change in motion sets up first the idea with momentum being a mass times the velocity, then a change in momentum being a mass times a change in velocity, and then we're looking at a time rate of change of momentum. Gives us the idea that this time rate of change of momentum, delta p over t, is equal to mass times an acceleration, which is what we commonly call a force. Now, this is what I oftentimes will refer to as the short form of Newton's second law. The idea of a change in momentum is oftentimes listed as a J, but this is an impulse. This is called an impulse. And then the third law gives us that momentum is always conserved. In other words, the change in momentum, if you look at everything, is zero. The momentum before is always going to equal the momentum after. We're going to discuss and look at the idea of free body diagrams. We're looking at pictures mostly from your textbook of how to approach free body diagrams. Some folks have particularly strong opinions about what a free body diagram should look like. In general, my view is it should be enough, and that's what it should be. So you're going to sketch it. You're typically going to indicate your forces with arrows. You want it roughly to scale. Label where your angles are. And in some cases, I typically like to go ahead and label the magnitudes of my angles and my forces and so on. Some folks put in more detail with making things like boats look roughly boat-shaped. Often my boats are rectangles. Another example of a free body diagram is down to pretty simplistic stuff. Here we're seeing that the angles aren't really even indicated, they simply are. Here it's indicated by a theta. You don't see any magnitudes in this picture. That's another approach to a free body diagram. This one has the free body diagram to the left of another representation of it, and then an even simplified form of a free body diagram where it has nothing but a point and two arrows indicating the direction of the forces. Well, this one isn't really a free body diagram, but it's another form of diagram. Well, this is springs, and we will talk about springs later on. This does give you an idea of which way forces and so on can be indicated. Here we see a fairly elaborate situation. We have the weight indicated, we have the normal force indicated, we have the force from each of the children that is pushing, you have the force of friction, and then you have in a different color an arrow representing the net acceleration. You see something similar down here in the bottom diagram. The middle is more of a representative of a force vector diagram, and then these are what some would consider more of a free body diagram. Again, some folks are very, very opinionated. I think it needs to be what it needs to be. So let's look at the idea of friction. Friction comes about because of the irregularities on the small scale between two surfaces. Often I will write the idea of the coefficient of friction as mu sub box is equal to F sub F over F sub N. This is the force of friction. This is the normal force, in other words, the force perpendicular to the surface. And I'll put a box here because we're actually looking at two kinds. We're talking about kinetic friction, and then we're also talking about static friction. And they're both the ratio of the force of friction to the normal force, but they're indicated as mu sub k or mu sub s, respectively. And here you can see a diagram, or a table rather, listing some forces of friction between various surfaces, both for static and for kinetic friction. When we're talking about friction, essentially what happens is the idea of static friction ultimately will give you a maximum amount of static friction that the two surfaces will resist. If you've ever tried to push anything heavy, you'll know that you can continue to push harder and harder until it finally breaks loose and starts to move. That's where you get this discontinuity idea right here. And at that point, we go from the realm of static friction to the realm of kinetic friction. The form of the expressions are the same, but the activity that's going on is different. If we look at an example of a vector type problem before we get into some friction, we have a situation where we have two individuals, Andreas and Kaya, pulling a wagon. Andreas is pulling to the northeast, which would imply 45 degrees from the x at 50 newtons, and Kaya is pulling in the southeast at 45 degrees with the same force. If we were to resolve both of these vectors separately into their components, we would end up with 50 newtons times the sine of 45 degrees and 50 newtons times the cosine of 45 degrees. If we were to do that for the one going to the southeast, we would end up with 50 cosine of 45 degrees and 50 sine of 45 degrees. Now in this case, in our diagram, this one is going up and this one is going down. Since they are the exact same size and 180 degrees opposite in direction, then they're going to completely cancel. So your net is simply going to be these two right hand or right facing components. So you're going to have your net, and I oftentimes will just go ahead and write the word net for your net force of 50 cosine of 45 degrees plus 50 cosine of 45 degrees, which is 100 cosine of 45 degrees. Since 45 degrees has a cosine of 0.707 approximately, this is going to give us 70.7 newtons. The question asks for the acceleration in the direction of motion of the wagon. So our acceleration, our net force, is mass times our net acceleration. Our net force we know is 70.7 newtons. Our mass is 23 kilograms. And so our net acceleration is going to be 70.7 divided by 23, or approximately 3.07 meters per second squared. And based on our diagram to the right, or east,